So in this part of chapter 1, we will talk about hybridization. I just want to focus on hybridization in this presentation. Again, you did hybridization back in Gen Chem 1, so you may want to refer to that textbook also if you still have it. If not, then you'll find that in your organic textbook as well. There are a few theories about bonding. The first one that you have learned about has been Lewis theory. And the Lewis theory is about sharing electrons in the valence shell, which means that the valence electrons are the ones that are being shared and bonded. Okay, so that's all we talk about in Lewis theory is how these valence electrons are bonding. The second theory that we talk about is usually the valence bond theory, and this helps the previous theory. Obviously, the first one did not work very well. That's why the second theory came around, the valence bond theory, and it helps a little bit with some of the points that the Lewis theory did not explain, which I will tell you in the next slide or so. And the third theory, which we will cover last, is the molecular orbital theory. Okay, so those are the three theories that we have for bonding. The main focus of this presentation is just hybridization. Okay, what you need to remember about bonding is that when a bond forms, you have electron sharing going on. What we talk about in Lewis theory, okay, is that electrons are being shared. We do not talk about where these electrons actually exist, meaning that do they exist in the S or do they exist in P subshell? Where do they actually exist? So we don't talk about that. So in valence bond theory, we will talk a little bit about that because it is an important part of bonding since we do have the subshells where the electrons exist. So that's what we'll next slide. Here you have a simple molecule, methane. Okay, I want to take this one because it's a really nice example for showing the importance of the valence bond theory. Okay, so you have carbon, okay, which has 2s2, 2p2 as its valence electrons. Okay, and so the two electrons, which are the s electrons, are these ones. Okay, the white one here and then the white one here. Two electrons in carbon are the p shape. Okay, and so this is here and here is the second electron. All these four electrons are being shared by hydrogen. Hydrogen is 1s1, so which means that all the orbitals are spherical for hydrogen. Those are these gray ones over here. So here is the bond overlap that's going on. Okay, and technically speaking, in Lewis theory, we don't talk about this overlap. We just say electrons are being shared. We don't really talk about the shapes that much. But if you look at these shapes of these orbitals, how they actually exist, they look a little weird, okay, in the sense that these s orbitals here, they have a nice good overlap going on, but the p and the s don't have such a good overlap going on. So which means that this bond may actually be weaker than this bond, okay, where you have an ss overlap, that might be a stronger bond than the sp overlap. The second thing about this is the bond length. In case of bond length, the SS overlap, because it is so close, the orbitals are pretty much alike, they will have a better overlap and therefore they will be shorter than the SP overlap. Okay, so which means that technically what we're saying is that methane has two different kinds of bonds. Okay, short ones, long ones, strong ones and weak ones. Okay, and technically and in reality that's not the case. All right, um, all the four bonds for methane are the same energy, they are the same bond length, so it doesn't hold up. Okay, Lewis theory does not hold up for that reason, and hence we have the valence bond theory, okay, which helps to explain a little bit about how the bonding actually occurs. So in the valence bond theory, which is about hybridization, we talk about mixing orbitals, okay? And so the way we deal with the hybridization is we give it the name of the orbitals that we are mixing, okay, together. So if you look on this side, it's all sp, sp2, sp3, sp3d, which means these are the orbitals that are mixing together. So for example, let's take the first one where you have the 1s orbital and the 1p orbital. So when you mix these two, you end up getting two sp orbitals. Remember, you're mixing two orbitals, so you should end up getting two. The best way to visualize this, if you can, is by thinking of these electron orbitals as clouds. And so if you have these clouds, the clouds will mix together. And once they're mixed together, you can't really differentiate between the S and the P anymore. And then once they're mixed together, hybridized together, then they will separate out into two. Okay, and so you will have two of the sp orbitals. The sp then, both of them will be alike. Okay, so they will not be different at all. That's the whole point about hybridization, is that it's completely mixed together. One s orbital and two p orbitals will give you three sp2 orbitals, because you're mixing one s and two p. When you look at the sp2 orbitals, that really means that you're mixing 1s and 2p orbitals. Okay, don't think so much about how many electrons there are in there. We will talk about that later on, because there are some cases which have a little bit of a different way to hybridize, and some electrons don't get hybridized. Okay, so we will talk about that also. So for example, when you look at sp3, all you need to think about is that you have one s orbital and three of the p orbitals that are mixed together, and so which means you should have four orbitals. Okay, that's about it. So then you have the other two also, where you have sp and d orbitals mixing. These two bottom over here, these are usually found for expanded valence shell. And since in organic chemistry we don't really deal so much with the expanded shell, we deal primarily with the carbon atoms. This is the max that we will go, which means four orbitals. Okay, so I will not be dealing so much with the sp3d and the sp3d2 hybridization. Let's start with the sp, okay, hybridization. And as you can see, this is quite a busy slide, so I want to take you through everything. The way you draw beryllium chloride, which is an example for sp, is this way. Okay, so beryllium bonded to two chlorines, sharing electrons, and then equal and opposite apart. And the way you got that equal and opposite apart is from the VSEPR theory, the Vesper theory, that you learned again back in Gen Chem 1. So according to the Vesper theory then, the Cl atoms are going to be far apart from each other, and they are linear. Okay, and both bonds are completely equivalent. In this case, they're equivalent. Okay, but here the shape is linear. So the way to explain according to the hybridization theory is that beryllium is in ground state, which is 2s2. Okay, and you can look at the periodic table to figure out what this electronic configuration will be. So ground state of beryllium is 2s2 electrons. In the excited state, which means that's where the bonding is actually going to occur, one of the electron jumps to the p orbital. Okay, and so which means that each orbital is singly occupied, okay, or occupied by single electrons. Now see over here, these two orbitals are empty. Okay, what we're going to do now with the hybridization is take these two orbitals which have these two electrons, the one of the s and the one of the p, and the one electron just happens to have one electron in each of these orbitals, and mix them. Once you mix them, hybridize them, again just think about the clouds coming together, going apart, and then you have hybridization. And that gives you these two new orbitals, okay, which are sp orbitals now. The two p orbitals are still there. These are going to be unoccupied, vacant orbitals. They're still there, okay, and they have their own function, okay, as well, because they can still have electrons. They just don't have any, but they can. The sp orbitals are the one that have the electrons in them, okay, and so now this is what the new hybridized orbital will look like. All right, so where you have the green ones, the green ones are the hybridized ones, and the clear ones here, okay, or the white ones, these are not hybridized. Now, if you look at the shape of the clear and the green one, there is a slight difference. Slight difference meaning that the green one is a little bit thicker, fatter, and that is because the P is mixed with S, and so the P got a little bit character of the S, okay, and so it looks a little bit different. But anyhow, this is what you end up getting as the new hybridized orbital. So then when you start forming the bond where you have BeCl2, so you have beryllium, which looks like this because it has the sp and the 2p. This is empty, so this is not bonding. And then you have the two chlorines, which is 3s2, 3p5. So which means you're going to have a p sp overlap, okay, to give the beryllium chloride. And then this is what the structure looks like then. Okay, so here is chlorine, here is beryllium with the hybridized orbitals, Here's the overlap happening, and then you have the two chlorines on either side. Bond angles here are 180 degrees, okay, because the shape is linear as we talked about before. Now for sp2, the example that we're going to take here is boron trifluoride, BF3. Boron is a nonmetal, 3 bonds. This is what the Lewis structure would look like. The VSEPR, the Vesper, is this way, which means that the shape is trigonal planar. Again, all bonds are equivalent, okay, in this case. So then we get started again with the ground state. Boron is 2s2 and 2p1. Now we have 1 electron in the p subshell. What's going to happen then? Excited state, remember, the s electron is going to jump to the empty p orbital. So now each orbital here is occupied singly. One of them is left empty because there are not enough electrons. Hybridization occurs for all the electrons over here, which means one of the electrons in the s and 2 of the p orbitals over here. So each of them have single electrons. So you end up getting sp2 hybridized orbitals, each of them having 1 electron. Okay, and then here this one is empty. And again, this has an important function. Okay, not to forget that. Now what's happening is that you still have some S character in the P. Now it's a 33% character of S and 66% of the P. In the previous one where you had SP, it was a 50-50 character. Now you have a 30 and 60, 33, 66 kind of a character of SP. Okay, so this is what the new hybridized orbital looks like. You have 3 lobes, okay, for this one, because there are 3 sp2 hybridized orbitals. So here is what all the bonding looks like. You have the 3F, again 2s2, 2p5, that's the electronic configuration for fluorine. Boron now is the hybridized atom, and sp2, sp2 hybridization. So the overlap is for p, sp2, okay, over here. This p orbital is still there, by the way, okay. You can see that in the final structure here also, and even before bonding, okay, it's still there. Is just vacant, okay, it's empty and it can hold more electrons, okay. So this is what the structure would look like, and the bond angles here are 120 because remember their shape was trigonal planar. One of the things to remember about hybridization is that hybridization is only for the central atom. Usually the terminal atoms, which in this case are fluorine, will not undergo hybridization. So essentially it's just for the terminal atoms. Hybridization is for the central atoms. Let's look at sp3 hybridization now. This is how we got started in the beginning, okay, when I showed you the methane and the 2 different bond lengths and the bond energies for carbon-hydrogen bond. So let's start again as usual. This is the Lewis structure for methane. You draw the Vesper structure, and this is what it looks like, which means it is tetrahedral, okay, and the shape is tetrahedral, and all bonds are equivalent, okay, over here, technically speaking. Okay, how do they become equivalent, right? That's the whole thing about hybridization. So again, we start with the ground state, and the ground state for carbon is 2s2, 2p2, okay? Excited state, 1 electron jumps from s to p, and so you end up having 1 electron in each of the orbital. Now what's going to happen is hybridization, where you mix the s orbital with the 3 of the p orbitals and mix them nice and get 4 orbitals, which are sp3 hybridized. Now again, remember, now you're mixing 4 orbitals, mix it together, separate it out together, and so then you have 4 orbitals, okay, and this is the hybridized state then. This is a nice visual of what it would look like. And again, these green ones are the hybridized orbitals, not really quite looking like the S or the P, okay, and that's because now we have 25% S character and 75% P character, okay, in this. So the orbitals don't look anything like what you would have originally, okay, mixing together. So now carbon with the sp3 hybridized orbitals and hydrogen, which is 1s1, bonding together. This is what it would look like. Okay, carbon here, all hybridized orbitals, no empty orbitals left over here. Hydrogen comes along. Here is the bonding. All bond angles are 109. Why? Because it is a tetrahedral shape. Okay, and so this is sp3 hybridization. So how do we do hybridization? Okay. Um, what we did, or what I did for you so far in the previous slides, was that I knew the examples for SP, SP2, and SP3, so I started with something that was known. But how do you figure out the hybridization if you don't know what the molecule is? Okay, and so I can give you any random molecule and ask you what the hybridization would be. In that case, what you need to do is follow these rules. Okay, first of all, draw the Lewis structure. Again, Lewis structure is the key for everything. So draw the Lewis dot structure, okay, of the compound, and this should be right. If this is not right, everything else is going to be wrong. Use the VSEPR to determine the electronic geometry. Okay, electron geometry about an atom, the central atom, is the number of electron groups you have. Okay, so whether you have one electron group or two electron groups, that's what it will be. From the electronic geometry, then you can figure out what kind of hybrid orbitals you have. Remember, for sp hybridization, you need two electron groups. For sp3, you need three. sp4, you need four electron groups. It's as simple as that. Okay. All right. And then you can draw the hybridizations. Here it is. Okay. Yet again, Lewis structure, number of electron domains, type of hybridization. So if you have two electron domains, it is sp. Geometry is linear. Three electron domains, sp2, trigonal planar, so on and so forth. Okay, this is how it should be. All right, for hybridization, it is as simple as that. So don't try and complicate anything. All right, keep it as simple. Just look at the electron domains and then figure out the hybridization. It should just work all the time. Here are the different shapes for the hybridized orbitals, a little bit more detailed than the previous slide. sp is linear, 180 bond angle. sp2 is trigonal planar, 120-degree bond angle. sp3 tetrahedral, 109.5 or 109 is fine too, bond angle. Trigonal bipyramidal is when you start having the expanded valence shell. So this is sp3d, and then octahedral is sp3d2. Okay, so these two shapes, these are for the expanded valence shell. Again, we're not going to be using this so much. Okay, we are going to be sticking a lot more with the linear, trigonal planar, and tetrahedral shapes. Let's look at solved problem for now. So if you have this structure given to you and you're asked to figure out what the valence bond theory is, okay, around here, which means what is the hybridization, okay, on this one. The best thing to do is figure out the electron geometry. And electron geometry for me, the way I work it is the Axe formula. And the Axe formula is where you have A as a central atom, X are the number of terminal atoms, and E is the lone pair of electrons, okay, that you have. That's the Axe formula. So you look at nitrogen, which has three terminal atoms, F, F, and N. N is not terminal, but it is terminal for nitrogen, okay, which means how many bonded atoms do you have? So you have three of those, and then you have a lone pair of electron over here, okay. So the Axe formula for this central atom is AX3E. Okay, AX3 meaning that there are four electron groups. How? 3 plus 1, 4. Or you can just look at the structure. 1, 2, 3, 4. Four electron groups. If you have four electron groups, then the only hybridization possible is sp3 hybridization. Okay, because that's the one that has the tetrahedral shape. Okay, it's as simple as that. Four electron groups, sp3 hybridization. And for multiple bonds, again, keep it simple, don't complicate it. Okay, so if you have carbon dioxide, you have two electron groups, okay, which means you have two bonded atoms. So then the Axe formula for carbon dioxide is AX2. A is the central atom, X is the number of terminal atoms that you have. Remember, you don't count the lone pair of electrons for the terminal atom, okay? When you're looking at hybridization, focus on the central atom. So if there are any lone pairs on the central atom, then you count them. Terminal, do not count, okay? So electron geometry is AX2. If it is AX2, it means you have sp hybridization. Why? Because you have two electron groups. Shape is linear, okay, for this one. That's literally how simple this can be, okay? Don't make it harder than that. Again, HCN, another molecule, multiple bond. Okay, this one is a triple bond now. And in this case, carbon is the central atom. Without looking at the answer, just focus on this. Okay, so carbon is A, X2. X2 meaning you have two terminal atoms. So if you only have two electron groups, then the shape is linear. If the shape is linear, hybridization is sp. Okay, it's as simple as that. That's how I work through all my hybridizations. Here is another solved example for you. So what is the hybridization on the central atom in a nitrate ion? Okay, and so here's the Lewis structure for nitrate. Keeping it simple, just focus right here. Okay, don't look at the answer. So nitrogen, 3 electron groups. Okay, no electron pair left, which means it is AX3. That's the electronic geometry for this, or that's the X formula for this. So AX3, if it is 3 electron groups, it must be sp2, because sp2 meaning you have 3 orbitals there. So what we did previously was all single bonds, okay, sp, sp2, sp3, and the examples that I took for you, those were all single bonds. You can figure out the hybridization for multiple bonds also, which we just practiced. So how does the hybridization work for double bonds and triple bonds? That's what we're going to cover now. A lot of the simple atoms, they will have a very simple overlap like hydrogen. It will have a simple SS overlap. If you have a little bit more complex, a triatomic or a polyatomic compound, then you will start seeing hybridization, okay? And so most of the single bonds are going to be hybridized. Remember, hybridization is only for central atom. It's not for terminal atoms. So all hybridized orbitals, they're called sigma bonds. Single bonds, the ones that we have dealt with so far with the beryllium chloride, was it barium chloride or hydride, or boron trichloride, and then methane, all of those were sigma bonds. Okay, that's all we dealt with. When we have a double bond, then we have a sigma bond, which means a hybridized bond, and a pi bond. The pi bond is coming from the unhybridized orbital, which is the overlap of p orbitals, okay, which have not hybridized, all right? So which means that it is a different kind of bond than a sigma bond, all right? That's why we call it a pi bond. In a triple bond, one hybridized orbital, sigma, and then two pi bonds. Okay, so we'll see some examples now. Ethylene, here we have a carbon-carbon double bond. This is what the structure looks like for ethylene. Now, without doing too much of calculations over here, look at the central carbon, 1, 2, 3. 3 electron domains. If you have 3 electron domains, it means that you have sp2 hybridization. So at least we know what our starting point is. Okay, so sp2 hybridization meaning here is the ground state, here is the excited state. In the excited state, you have to mix sp2, one of the s and two of the p orbitals. So when you mix the one of the s and the two of p orbitals, one p orbital is left behind. Okay, and so here are the new hybridized sp2 orbitals, and here is the poor unhybridized orbital, okay, p left behind. Okay, so then this is what carbon looks like now, all right, where you have the gray orbitals, which are going to be the hybridized orbitals, and then the p, which is the blue one, okay, that is left unhybridized. This is what the structure looks like, okay, when you have ethene, okay, or ethylene. When they combine, this is what you have, all right. So the green ones, again, remember, the green ones are the hybridized orbitals. The blue ones here now, this is the p orbital, okay, right here, which is the unhybridized, and then the hydrogen, which is bonded to all the sp2 hybridized orbitals, okay, from the central carbon. What happens then is that since you have these two orbitals, the p here and the p here, which has not hybridized, they tend to delocalize over each other, okay, and they end up forming what is called then the pi bond. Now, this might be a little misleading for you in thinking that you have 1, 2, 3 bonds. Please do not think of it like that. The pi bond is considered to be one bond, okay, over here. Why? Because there is one p orbital here and one p orbital here. Okay, so if you have these two overlapping, you will get only one bond, okay, between them. So a double bond will have one sigma bond and one pi bond. Okay, that's what this is. And we will encounter this a lot in organic. So wherever you see a carbon with a double bond, no matter what it is bonded to, whether it's a carbon, a oxygen, or a nitrogen, it doesn't matter. So long it has a double bond, it will be sp2. Let's take a look at another molecule now. This is acetylene, and acetylene has a triple bond, okay, in it. So you have carbon-carbon with a triple bond and then bonded to the one hydrogens. Again, without looking at anything else, just focus on this carbon. This carbon is the central atom, and here are two electron domains. So if you have two electron domains, it means that the hybridization is sp. So which means that when we do our hybridization chart, we know how many electrons to mix, okay, or how many orbitals to mix, excuse me. So here is the ground state of carbon, nothing new. Excited state, nothing new. The s electron has jumped over to the p orbital, but now what we're going to do is we will mix only one s and one p orbital. Which one you choose, it doesn't really matter, okay, because remember all the p are what we call degenerate, okay, which means equal in energy. So it doesn't matter which p orbital you choose, just choose one and you mix those two, all right, which means that the other two are now left over. So now here we have the two mixed orbitals, the sp orbitals, which are down here, and the p, which are unhybridized, and they're up there. Why are they up there? Because higher in energy, okay, the sp are a little bit lower in energy because of s being lower in energy, so it brings it down a little bit. So now we have two electrons left over that are unhybridized and two electrons that are hybridized, and this is what the carbon looks like, where you have two of the p orbitals, and the gray one here is the hybridized orbital, okay, and the blue and the green, those are the p orbitals. Okay, and here is the shape, the structure, okay, of this compound, where you have carbon. Remember, the green one again is the hybridized orbital. Hydrogen is bonded to the hybridized orbital, which means that this is a sigma bond going on, okay, with the green one. The bond overlap here for hydrogen and the green one, the carbon, is sp and s, okay. Here are the p orbitals that are left over, and since they're left over, they're going to overlap with each other. Since you have one p orbital here and another one here, which means two on each carbon, those two will overlap to give two bonds, okay, and so two pi bonds and then one sigma bond, okay, that makes up the triple bond. So wherever you have a carbon with a triple bond, you will always have one sigma bond and two pi bonds. That's a given. Now let's look at some of the properties of the different kinds of hybridizations that we've talked about, specifically the single, double, and triple bonds. Okay, so ethine is triple bond, ethene is double bond, and ethane is single bonds. Okay, so let's look at the bond lengths and bond energy. Okay, for all of this, remember I mentioned to you in the beginning that the whole point of hybridization was to make sure that all bonds are equal, okay, in energy and all that good stuff, especially for methane. So anyhow, let's look at the bond strength first. So the bond strength for CC bond, okay, which is sp3 hybridized, is 377. And then as you go on further on to hybridized orbital, which means going from sp3 to sp2 to sp, meaning 25% S character to 33% S character and then to 50% S character, the energy of the bond increases. Okay, this may have something to do with the bond length. Okay, because if the bond length is shorter, it means that the bond strength, okay, is good. All right, the overlap is very good. So here we have the bond length for CC bond sp3, it's 154. For sp2, it's getting a little shorter, and then with sp, with the triple bond, it's getting even shorter. Okay, and so as the bond length gets shorter, it means that the overlap is getting better and better, and therefore the bond strength keep increasing. Okay, so which means a triple bond is stronger than a double bond, which is stronger than a single bond. Okay, that's how it goes. Here is a little summary. And I would highly suggest that you go to this website over here. It really shows the hybridizations going on very nicely, okay, in a nice animated format. So go ahead and check this one out. This is your summary, and these are the properties that I really need you to remember for this course, okay, and the next one, organic 1 and 2. So sp3, sp2, sp hybridization, I've given you the shapes, the bond lengths, angles that you need, so on and so forth. Okay, this is all the properties that you should know for hybridization. Here are some solved examples, okay, for these questions. How many pi bonds and sigma bonds are there? And so carbon, sp3 hybridized over here. Why? Because it is all single bonded. This carbon is double bonded and therefore it is sp2. And here you can see in this large molecule that because carbon here has so many different kinds of bonds, you can have different kinds of hybridizations. So where carbon is a single bond, it is sp3 hybridized. When it is double bond, it's sp2 hybridized, and triple bond is sp hybridized. Okay, so you can have different kinds of hybridizations going on. The molecular orbital theory is the last theory that we talk about in bonding. And the molecular orbital theory is even better than valence bond theory in explaining a lot of properties. And we talk about molecular orbital theory a lot more in organic too, but I want to introduce a concept to you, okay, of how this actually works. This is also called in short form MO theory, okay? And what really is happening in MO theory is that when you combine two orbitals, which are called atomic orbitals because they're not bonded yet. So when you have two atomic orbitals bonding, you end up getting the same number of bonding orbitals. In the same number of bonding orbitals, you get two kinds, okay? One is bonding and one is anti-bonding. Anti-bonding are higher in energy, bonding are lower in energy. So the electrons are usually found in the bonding orbitals, the anti-bonding is empty. Okay, so it's a little bit different. It's a little bit different kind of a theory. Here is an example, okay, of how this works. And hydrogen is a simple, nice molecule to work with, where you have one s1 and one s1 electron. That's it, only one single bond here. So that's why I give the example only for this one. So here you have two atomic orbitals, which are one s and one s, okay? Atomic orbitals, not combined yet, okay? And then they combine. So now we have what is called an antibonding orbital, and here's the bonding orbital. Remember, in the 1s and the 1s, there's only one electron, okay, each, which means this hydrogen brings one electron. This hydrogen also brings one electron. When they combine, each orbital can have up to two electrons. So the two electrons that you find in hydrogen are found actually in the lower orbital, okay, lower bonding orbital. The higher one, which is called the anti-bonding, is empty then, okay, because as it is, it's too much higher in energy. So the lower energy one is usually the occupied one. We will talk a little bit more about this in organic 2, not so much in organic 1. You need this to understand some spectroscopy, but most times we can get away with valence bond theory in organic chemistry. Here are the things that you need from this chapter: the valence bond theory, hybridization. Yes, hybridization, all of it. sp, sp2, sp3, all the properties. That's the table that I gave you, and a little bit about molecular orbital theory. I probably won't ask you any questions in an exam for MO theory, but you know, it's just kind of be aware that there is one other theory. Okay, so these are your concepts that I need for you to get away from this little PowerPoint.